In-class activity 12D, optimization. Jean and Vanessa are making popcorn boxes out of 8.5 by 11-inch sheets of cardstock. They decide to cut squares out of each corner and fold up and tape the sides to make rectangular boxes. 1. Jean cuts out 2-inch squares while Vanessa cuts out 1-inch squares. Which box will hold the most popcorn? So it mentioned Jean first, so we'll just do Jean first. Jean is cutting out 2-inch squares. All right, so along the side, the shorter side, 8.5 inches. So we have 8.5 minus 2 plus 2 is 4. So this ends up being 4.5 inches. That's left here in the center. We'll do the same thing along the top. We have 2 inches and 2 inches. And then we have 11 to start on the long side, minus 4 inches. And this ends up being 7 inches. So 7 along the top. So volume is length times width times height. So if we take the 2 times the 4.5 times 7, 2 times 4.5 times 7 is 63 cubic inches. Now let's do the same thing again, and let's do this in a different color. So I'll do a different color for Vanessa, and let's take out some of this information for Jean. Oops. There we go. So Vanessa. So Vanessa is taking out 1-inch squares here and here. So that's going to be 8.5 minus 1 and 1 is 2. And that's going to be 6.5 left in the center there. And let's see, a 1-inch square here along the top and the top. That's 11 to start minus 2, and that gives us 9. So Vanessa, length times width times height is 1 times 6.5 times 9. 1 times 6.5 times 9 is 58.5 cubic inches. So comparing these, Jean is at 63, Vanessa's at 58.5 cubic inches. Looks like, to answer the question, which box will hold the most popcorn, it's going to be Jean's box. Okay. Objectives for the activity. You will understand how changing the dimensions of an object affects its volume, that design problems can have optimal solutions. You will be able to construct a polynomial function to model the volume of certain objects and use models to decide what the optimal dimensions of a container should be. 2. Consider the method for constructing boxes in question 1. Let X represent the side length in inches of the squares that are cut out of each corner. Part A, as X increases, how does the height of the resulting box change? So as X increases, we could say the height of the box increases by the same amount. The height of the box also increases by the same amount. There we go. Part B, as X increases, does the area of the rectangular base of the resulting box increase, decrease, or stay the same? So as X increases, the area of the base decreases. All right, part 3. On the diagram shown, label the dimensions of the rectangular base of the resulting box in terms of X. So let's scroll up. I'm going to scroll up so that 3 is, you can still see 3. And there's our diagram. So on this diagram, we want to label the dimensions of the rectangular base of the resulting box in terms of X. All right, so what we drew earlier in the first examples, we have, instead of numbers here, the 1 or the 2 that we put in for Jean and Vanessa, we're going to let that be X. So the shorter side is going to be 8.5 minus 2x. And then the longer side, it starts out at 11. So that's going to be 11 minus 2x. Part 4. I'm going to scroll up a little bit. Part 4 says use your diagram from question 3 to write a formula for a function v that outputs the volume of the box in cubic inches as a function of x. So we're going to do volume. So v of x, it's going to be equal to the height of the box there, x, times 8.5 minus 2x, and then 11 minus 2x. Part 5. Use a graphing calculator or app to view the graph of v of x as x ranges over the possible sizes for the square cutout. How big should you make the square in order to maximize the volume of the box? What's the largest volume box you can make using this construction method? So let's go to our calculator. And I have this entered in the y equals screen. It's under y1, so I'm going to turn that on. And if we graph that, you can see the curve that we have here. And how big should you make the square? And what's the largest volume? We can answer this about at the same time. I'm going to scroll up to the highest point there. And you can see when x is about 1.59, that's the highest part of the curve. Y ends up being about 66.1. So these are the two answers to our question. Let's go back to where we were. Remembering those numbers, the volume, we'll put volume is maximized at x. It's approximately we're going to round to 1.59. And then, the max volume. The max volume is about, we're going to round to 66.1, and that's cubic inches. Part 6, Gene and Vanessa decide that they are going to fill up their popcorn boxes with heaping portions of popcorn that extend in a mound over the top of the box. We can model the volume of a heaping portion of popcorn by placing a pyramid on top of the box. Let's assume that the height of the pyramid is 25% of the shortest side of the rectangular opening of the box. And it says, see the drawing. So here's the drawing. I'll leave 6 at the top so we can see the question and the drawing. And part A, it says, modify your volume function to account for the extra popcorn in the shape of the pyramid. Recall that the volume of a pyramid is 1/3 the area of its base times height. So we're going to call this function, we'll call it v sub h. And then we have v sub h of x is equal to, well, we have whatever is inside the box already. We calculated that as v of x plus, recall the volume of a pyramid is 1/3 the area of its base times height. So let's multiply this by 1/3 times 8.5 minus 2x times 11 minus 2x, and it's 25%, so we're going to write that as a decimal, times 8.5 minus 2x. There we go. Part B. If Gene and Vanessa want to maximize the amount of popcorn in a heaping portion, how big should the square cutouts be? Use your modified volume function to determine the optimal cutout size and the maximum volume of a heaping portion. So let's do the same thing that we did earlier. We are going to go to our calculator here. We're done with this. What I'm going to do is go back to y equals, turn off the y1 screen, and turn on the y3 screen. I have that last, the v sub h function entered in under y3. So let's graph that, and Let's just go up to the max here. And we can see when X is about 102, our Y reaches its maximum output at about 90.2. So let's go back and answer our question. And it says, if Gene and Vanessa want to maximize the output of popcorn in a heaping portion, how big should the square cutouts be? Well, that's the number on our x-axis. So the x was about 102 inches, or excuse me, 1.02 inches. So the heaping volume is maximized when the cutout size is approximately 1.02 inches. And part C, compare this with your answer to question 5. Does the modified model predict a different optimal cutout size? Does it make sense that the optimal size is different when the heaping portions are considered? The answer would be, let's see, we'll put yes. And then the model is predicting. So let's see, how about the modified model? So I am just going to squeeze that word in here, just rewrite it. The modified model predicts a difference optimal cutout size. So the modified model predicts a different optimal cutout size. The maximum heaping volume is approximately heaping volume is approximately 90.2 cubic inches. Period. And then it makes sense that that the boxes should be shorter because a bigger opening, if we think about this, a bigger opening gives more room for the heaping portion over the top of the box. So yes, the modified model predicts a different optimal cutout size, and the maximum heaping volume is approximately 90.2 cubic inches. That's the end of this video. Thank you.